Okay, are you guys able to see
You want to press
my
the
tab?
Yeah, I can see it.
Great. Okay, so yeah, thanks guys for inviting me to this journal club. Yeah, I'm really happy that we connected through Create. I've met Jamal before. I don't know if I've met everyone else, but this is great. So I'm going to tell you guys a little bit about shallow and undoped germanium quantum wells today. In particular, Sammak et al. In 2019, they measured a particular material, and this involved a 22 nanometer deep quantum well in silicon germanium heterostructure. So let me explain a little bit of what that means. I'll start with background, then I'll talk about the silicon germanium heterostructures that we are interested in. Then I will talk about these HFETs, or heterostructure field effect transistors, that were actually fabricated by the authors, and then the characteristics that they measured for these materials. Okay, so this is one of the central claims of our paper that we're considering today, that basically a high mobility along with a percolation density that they observe, a light effective mass, and a high effective G factor highlight the potential of this material as a low disorder platform for hybrid quantum technologies, including quantum dots, which were, of course, useful for quantum computing. So first, we'll need to understand these terms, and I'll go through them one by one so that we can sort of understand this claim, which is the central claim of the paper, and how it can connect to quantum dots and to quantum computing through that. So I'm going to go over G factor, carrier density, effective mass, mean free paths, mobility, low disorder materials, percolation density, and the SDH effect, which will all help us to understand this paper. So first of all, I think most of you guys have probably heard of G factor. I know when I started my PhD, I heard it many times and had to look into exactly what it meant. But the G factor appears in our Hamiltonian when we're talking about the Zeeman effect, which provides the splitting induced by the magnetic field, which creates our two levels for our qubit. So spin-based qubits are quantum systems where the computational subspaces levels derive from the spin, which is, of course, the intrinsic angular momentum of an elementary particle. That particle should be isolated, and this is what our quantum dot does. It confines via a top gate a single hole or electron electrostatically. So our host materials can include silicon, germanium, and gallium arsenide. Gallium arsenide was sort of looked at earlier on in the field of quantum dots and then abandoned. Basically it has a poor T1 and T2 times. So what we want to have is longer coherence. And we are looking at silicon and germanium because they have longer coherence times. And this has to do with how silicon germanium, the nuclear bath, actually interacts with our electron or hole that we've electrostatically confined. And there's a lot of details that I won't go into, but this is the motivation for looking at germanium and silicon, or at least one of them. So an isolated single spin half particle in a magnetic field has the following Zeeman Hamiltonian, and I'm just pointing this out because we have G in here, which is our G factor. Here also mu B is the Bohr magneton, which is something I will derive in a moment, and we have our magnetic field as well as our spin. So quantum dots are often likened to artificial atoms since they can behave like a hydrogen atom, for example, with a single negative charge. And so we'll consider an electron orbiting a single proton since this is analogous. The electron in this picture has an angular momentum about the proton due to its motion. And as we know from quantum mechanics, this is quantized. We also have a magnetic moment. This is where mu comes in, which arises from its motion. And it is defined by the product of the bounded flow of current J with the area A enclosed by its loop. And here I show the formula for this current and how we actually get mu. So mu is just J times A, which is the area enclosed. And the formula for J is basically a function of the angular frequency of the electron and its charge. So we get a moment of inertia of the particle and the gyromagnetic ratio. The gyromagnetic ratio exactly relates mu and L. So that's the angular momentum and the magnetic moment. So experimentally, we can observe or indirectly observe the gyromagnetic ratio by measuring these two quantities. And we noticed before Dirac wrote his thesis that basically the gyromagnetic ratio for spinful particles was found to be twice this. And this was not understood until Dirac published his relativistic equation. And this relativistic equation provides us the correction to the gyromagnetic ratio, which we call the G factor. So we can get the Bohr magneton by quantizing L along an axis such as Z, which we do by introducing H bar. And it follows from Dirac's relativistic equation that the magnetic moment corresponding to an intrinsic angular momentum follows a similar logic, as I said. However, we get that factor of 2. So the factor of 2 here, if you notice, in front of the mu b m, is to basically give us the gyromagnetic ratio for spinful particles. But elementary particles don't just have intrinsic or extrinsic angular momentum. So they don't just have spin or extrinsic angular momentum, they have both. Therefore, we write G to capture this. And G has been derived basically through a long derivation that I won't include to be given in terms of quantum numbers S, L, and J. And this is the formula we get. But G, in this case, is a number. And this is because we've quantized along the axis Z. But in general, G is actually a tensor with X, Y, and Z components. Okay, so I've talked a lot about the G factor, and I'm almost done talking about it. But just to remind you exactly what's going on here with our quantum numbers, let's have a quantum number refresher really quickly. So two identical fermions, as you know, cannot occupy the same state because of the Pauli exclusion principle. Therefore, two identical fermions must be in different states. If fermions are in the same orbital, their terms must differ by a quantum number such as spin. And this is taken as an axiom in non-relativistic quantum mechanics, so I don't have to derive that. But the orbitals that constitute valence shells of atoms are degenerate. Each of their slightly detuned energy levels may be filled by at most two identical fermions of differing state, such as half and negative half, and therefore we count electrons in atomic orbitals by the following convention, which is review for all of you, but we have spin at the bottom, and then we have our other quantum numbers, m, l, and n, going to the top, which are given in terms of each other. And they're basically integers. So the G factor, given all this, is an important criteria for selecting host materials for spin qubits. Finally, connecting it back to quantum computing, since the eigenvalues of H give the energies of the spin up and spin down states for our qubits. The separation is determined by the G factor, and that separation energy, epsilon, is given here. You'll have the spin up state corresponding to one of these plus minus, and the spin down state corresponding to the other sign. So you can define that either way, but this is the energy separation. So we've covered the G factor, and we understand how it connects to quantum computing. So we're going to select a material based on its G factor so that we can have host qubits. But we still don't understand the claim that this is a low disorder material. So I will just quote from a book called Disordered Materials and let you know that a structurally disordered solid is an extremely complex system by definition. It is not crystalline, so it is not a perfect lattice, but at the same time, it's not purely random. So that is actually our definition for a structurally disordered solid. And that is what our authors claim they have found. The other definitions I will go through very quickly, so I won't go into as much detail as I did with the G factor, but I think the G factor is one of the most interesting or difficult to understand, so that's why I spent some time on it. Now I will just let you know that mobility is what we term the speed or the multiplier which gives us the speed of a carrier moving in an electric field within the material. The carrier density is the number of charge carriers per volume, The effective mass is the apparent mass in the potential, and this potential is the potential created by the material itself. So this is like the apparent mass of a particle traveling through the material. And that means we don't consider the actual mass me of our particle when we're basically writing dynamical equations. Instead, we consider m star, and m star helps us to basically simplify our equations so that instead of accounting for all of the electrons and nuclei and all of the interaction terms that we would have in a dynamical equation describing the motion of our particle, we instead just represent our particle as though it has a different mass, and this mass changes in order to summarize the effects of the basically crystal as a whole. Then we have mean free path, which is the distance traveled by a particle through the material without collision on average, and the percolation density, which is connectivity at the scale of the material. And greater connectivity at the scale of the material actually implies more order. So if we have more disconnected pieces throughout the material, we're going to have more disorder. And that connects back to our definition of disordered materials. So in the equations here, I've basically bolded the parts of the equations that actually relate to our characteristic. So for example, I have the drift velocity Vd in the first equation equaling m, the mobility, times the electric field, and m is our mobility. I've completely bolded a lot of these other equations because they just give the expression for example, carrier density, effective mass, and mean free path. Percolation density is given by this P sub P in this equation, which relates it to the conductivity. Okay, and please stop me at any time for questions because I'm just going a lot of concepts pretty quickly, but I'm going to move on. So finally, one thing that I need to help you guys understand in order to take a look at Landau fan diagrams and some of the other observations that the authors make is the SDH effect. I'm not going to try to pronounce that, but basically at low temperatures and high magnetic field, carriers in a conduction band can behave like harmonic oscillators. The oscillation period changes proportionally with the magnetic field, and the resulting energy spectrum is composed of these levels called Landau levels. They were discovered by Landau, and these are separated by a cyclotron energy and split by the Zeeman energy. So the number of carrier states in each level increases with the magnetic field as well. So the Landau levels move to higher energy as the magnetic field increases. And so you can imagine as these energies increase, they move through the Fermi energy. And when they do that, the levels depopulate, and the depopulated carriers create a current. And this effect yields a periodic oscillation in the material's conductivity and is called the SDH effect. So we'll actually look at the SDH effect to try and characterize our material since we can measure this conductivity. Now, before I go into the material characteristics and other observations, let me just give you some background on quantum dots themselves. So quantum dots are like field effect transistors, basically of channel type with a capacitive island. And the island is a 3 to 5 type semiconductor generally, and that refers to the 3 to 5 on the periodic table. So to load a quantum dot, we basically have to cross an energy barrier, and to load the nth electron or charge carrier, it's actually scaled by n squared. And this repulsion is referred to as the Coulomb blockade. However, carriers can tunnel through this barrier. So here's a diagram basically of a simple quantum dot. It looks like a field effect transistor with a source and drain. However, instead of just a channel between the source and drain, we have an island, which is a 3 to 5 type semiconductor. And then on top of this, we have a stack of a gate and an insulator. So the gate here would be some kind of metal where we would apply a voltage, which would change the energy barrier. Basically, a carrier has to overcome or tunnel through to get from the source to our island. So the source of our island can be modeled by the tunnel resistance and a capacitor. A voltage VB can charge the quantum dot until we reach an equilibrium, which would be VB equals VC at delta T equals RC. This being the tunnel resistance and the capacitor that models our island. And a discharge will also decay exponentially with the same profile. So we can charge and discharge our quantum dot. The barrier must be larger than the thermal energy for a carrier to remain bound to the quantum dot. And this is a really important detail. This is actually why we need to do our experiments at like either sub 1 Kelvin, which we often do, or 4 Kelvin when we're just screening devices. And it's exactly so that our thermal energy is less than our barrier, so that we can have our carrier remain bound to the quantum dot. So applying a voltage, as I said, to the gate lowers the energy levels of the quantum dot for carriers to populate, and this is how we can control our dot population. Then I have the equations just for the capacitor. C equals epsilon A over D. That's basically the parallel plate capacitor equation. And then the energy of the quantum dot here, energy stored in the capacitor here. So that's our background. Now I'll get into the actual SiGe heterostructures that the authors present. So the authors discuss germanium, silicon germanium heterostructure grown on a 100 millimeter silicon substrate in a high throughput reduced pressure chemical vapor deposition reactor. So a chemical vapor deposition reactor basically introduces a chemical vapor to a chamber and allows that chemical vapor to react with the surface of their material and basically deposit a thin film or a layer of material based on the exposure time. So their layer sequence comprises a particular silicon germanium alloy, which is a virtual substrate obtained by reverse grading, a 16 nanometer thick germanium quantum well, a 22 nanometer thick SiGe barrier, and a thin sacrificial Si cap. So a sacrificial Si cap basically is a thin layer of material at the top of your device where it would interact with the atmosphere or the air. And it's there basically to be sacrificial so that the material underneath doesn't degrade or oxidize as quickly. So they're allowing this sacrificial Si cap to interact with the atmosphere in place of the rest of the material stack, which is more important to them. So importantly, defects and dislocations are confined to the lowered layers. Dislocations, of course, are like basically when you have two materials, like for example, silicon and SiGe, that are on top of each other, or one is deposited on top of the other, you have lattices that aren't perfectly aligned. So our lattices will try to align at the interface, and that might cause some stretching of the crystal lattice and deformation. This deformation can lead to dislocations, which are basically fractures or breaks in the crystal lattice structure. And you can see these often with like an atomic force microscope or something like this. And they would be like cracks. They almost look like cracks in the crystal lattice. And it's important to confine these to the lower layers so that our upper layers of our material are not defective. So this is what their layer schematic looks like. Also scanning electron microscope images of their quantum well and their material concentration profiles, their interfaces, etc. So on the very left, I think the most important thing is this stack, which starts with the Si substrate, then they have GE, then graded SiGe, and the quantum well at 22 nanometers is the SGEQW. So this is what their stack looks like, and their paper is basically presenting the fact that they fabricated this. And then we have, in this image, concentration profiles, as well as stem images. So you can see how the SiGe is sort of concentrated towards the top in the middle. We start with 0% silicon, 100% germanium on top of our silicon substrate, and then we introduce SiGe in a graded fashion to get to our 20%, 80%. Yeah. Now we'll talk about the heterostruct field effect transistors that they fabricated. So these are the devices that they fabricate on top of their material. They devise a process for fabricating dopantless heterostructure field effect transistors. And we already talked about how a FET basically relates to quantum dots. A FET is very similar to a quantum dot. However, the quantum dot sort of quantizes the channel by introducing a small island instead of a channel. So the fact that they've manufactured FETs means that it's promising for quantum dots to be manufactured as well. And this, they say, establishes their material as a potential host for quantum dots and other quantum technologies. So a top gate would be used to isolate a single carrier in a 2D whole gas. To this end, when we were manufacturing a quantum dot, but they just have a 2D whole gas. Actually, they specify a 2D whole gas in their case, but I think it's arbitrary. So in the paper, this HFET is demonstrated. So basically, they deposit platinum allox, which is their dielectric, and Ti-gold for their top gate. They show the thicknesses here, as well as the shape of their HFET, which is very similar to like a Hall bar. Their Ti-gold is not just gold, because basically gold has problems sticking to dielectrics. So what we do in the industry and in the field in general is basically, instead of just depositing gold on top of allox, we first deposit a thin layer of titanium, like it's like 5 nanometers or something like this. And then we deposit the rest of our gold like 50 nanometers or something like this. So you can see the scale of their structure, and you can see where they have bond pads and omics and the rest. So this is their HFET. Their top gate has this interesting shape like a Hall bar. Then I'll go into the characteristics that they measured. So basically, they did a number of experiments with this HFET device. First, a negative DC voltage bias was applied to the top gate. Then a fixed AC voltage was applied to source and drain contacts. 4 probes, which you could actually see in the previous image, were used to measure the longitudinal and transverse components of the resistivity sensor rho. And these probes were also used to measure the longitudinal and transverse conductivity indirectly. The active carrier density and carrier mobility were measured via the Hall effect, and an effective G factor was found via observing SDH oscillations and spin splitting. So here are some of their results. So we have the conductivity sigma and the resistivity rho, and their voltage applied to the gate. So you can see how basically they were able to extract profiles for these and characterize their device. They have some other things here as well, but everything is in terms of either resistivity, conductivity, magnetic field, or carrier density. So we can go more into any of these graphs if you guys have any questions, but I'm going to keep moving along to talk about these color plots, which is their Landau fan diagram. So color plots of the resistivity as well as the transversal Hall signal at 50 millikelvin as a function of L-plane magnetic field and carrier density are shown. So they basically defined 0 to be blue and 10 to be red, and then they show this fan diagram showing how their carrier density responds to the magnetic field, and how the G tensor responds to the carrier density, or is defined in terms of the carrier density. So they calculate a carrier density of 1 times 10 to the 11 centimeters to the negative 2. Maximum mobility as well of 5 times 10 to the 5. And this corresponds to a mean free path of 6 micrometers. Percolation threshold density was established at 1.7 Kelvin. Again, they do these experiments at 1.7 Kelvin for the same types of reasons that I explained. We need to have our thermal noise not overwhelming the system and causing everything to misbehave. They calculate an effective mass and a G factor between 7.5 and 9.2. So let me show you a little bit about what I mean when I say they use the Hall effect. So the Hall effect basically maybe I'll go to this diagram first. The Hall effect basically is illustrated by this diagram. If you think about the structure of our HFET, we had this long bar sort of connecting from left to right our ohmics and our 4 points of contact for our measurement experiment. And what they would do in their experiment to measure the Hall effect is they would apply a current going across from left to right. And this would be perpendicular with the magnetic field, which in this case is going into the page. And due to the handedness of the magnetic field, charges would start to accumulate on either side of the bar here, which is why we call it a Hall bar. And so I've illustrated those in blue and red. And due to that accumulation of charge, we get an electric field, which is perpendicular to the current. We have a cross-sectional area, which allows us to specify the carrier density in terms of area. And this is what the Hall effect looks like. This electric field is in terms of what we call the Hall EMF, which is the voltage across this Hall bar from the top to the bottom. And we can calculate the charge density based on this. So our charge density N is going to be our current divided by the fundamental charge Q naught times the drift velocity times A. Our drift velocity is just going to be E over B. Since these forces have to cancel out for equilibrium to be reached in our charge carriers. And then the electric field inside the Hall bar is given in terms of the EMF, as I mentioned. So that allows us to calculate a lot of our figures of merit. And then they also calculate a G factor using this equation, which is estimated by comparing the field strength where the STH oscillations appear and the field strength at which spin splitting occurs. And here are my references. So the main reference, of course, is Sammak et al. At the bottom, but I also referenced the structure of disordered systems, as well as a few others. So that's my presentation. Thank you guys so much for listening, and please feel free to ask any questions.
Yeah, thank you, Marcus. I have a question actually. I think it was slide number 25 or something. I have two questions. One of them is related to that, which you are applying another layer after Tice Bolt. I was wondering if that changes the connectivity or the energy of the Hamiltonian, and how does that, how you're quantifying the changes based on adding that layer, extra layer.
I'm sorry, which slide was it? Was it this one?
Probably 26 or something. Yeah. I think it was 24, and my question is related to 20. Oh yeah. Go back 20. Yeah, here.
Here. Okay.
It is gold tie gold there.
Yep.
You explain that you are adding another layer to connect it to aluminum oxide.
Yep.
And I was wondering, how does that change your connectivity and Hamiltonian of the system?
Oh yeah, okay, so in terms of connectivity, AL023 is actually our dielectric. So it is an insulator. So we don't have any connectivity between the tie gold and the platinum underneath. Basically, what we want to do is we have this whole gas in our what's labeled as SGE here. This is our quantum well. This is 22 nanometers beneath the surface here. And we have this whole gas in here. What we want to do is we want to gate it by applying a voltage to our tie gold, which is our top gate. And that is creating an electric field, of course, and basically making it more attractive or less attractive for holes to populate the SGE in this region. And so, yeah, so basically, as you can see on the right-hand side, we have a wave function, and that is going to depend on the electric field penetrating this material when we apply a voltage to the tie gold. So
that's on the green width of the.
So we have heavy holes and light holes, they're called, and there's like a splitting between these, but these are basically two solutions to the wave function. So two steady states, basically, I suppose. And yeah, there's a lot of complicated like band theory into why we have LH and HH.
Which one is the solutions? LH and HH, you mean?
Yeah.
Because let's see your cursor if you're referring to something.
Oh, yeah, these.
Oh, yeah.
So you can actually make qubits with heavy holes or light holes in theory, but we have both in this system. So basically, we have a whole gas, and there's some like population of light holes and some population of heavy holes, and that refers to their effective masses, like whether they're light or heavy, and they exist in this channel. So we want to create a potential.
I cannot see
either
the cursor again.
Sorry,
I
cursor.
cannot see the cursor, yeah.
Oh, yeah. So we create a potential
Yeah.
that encourages them to occupy this channel or not.
Oh, I see, I see. Yeah. Gotcha. Yeah, and for the, I think it was last slide or something, they were talking about the EMF of the Hall effect.
Yes.
I think at the same time so you're propagating the electric field alongside the slab. That would generate the electric field. Sorry, you are propagating the current, and that would generate the electric field, and you're already having that magnetic field, which is applying. I think that is a bias field, or
Yeah, so we have a magnet, and this entire thing is in like some magnetic field, and yeah, so we just have a magnet turned on somewhere.
I see, and that would basically would be the Maxwell equation. I think that the EMF of Hall effect would be dB over dt, I guess, or that just comes from the current.
So it comes from the accumulation of charges on the top and bottom of our Hall bar. So we get this voltage across here because of the accumulation of charges.
Oh, I see. So that doesn't relate to Maxwell's equation?
I mean, of course it relates to Maxwell's equations because Maxwell's equations describe like all
Yeah,
electric fields, but in this case, it's quite a simple mechanism.
I see. Because when you're talking about EMF, probably that would be also changing the
I think the electrons, well, they're coupled to the magnetic field,
Oh, I see.
so they have different
Yes.
spins. So some go to one side, the
Oh,
other
I
half
see.
go
So
to the other side.
that actually depends on the magnetic
Yeah,
field.
and
Yes,
that
yes.
that
yes.
is like a
Gotcha.
capacitance, right? So you have
So, yeah.
electric field.
That makes sense because
Yeah.
just by applying the current,
Yeah.
it shouldn't change anything.
Yeah, the whole effect is that just electrons
I
or
see.
spins interacting with magnetic field,
Yep, exactly.
Yeah.
and you have this capacitance basically.
Mm-hmm. Yeah, that makes sense.
Yeah, exactly. Thanks for your questions. Is there anything else?
There's another question.
Well, just not related to the talk maybe, but well maybe it is. But you mentioned you work in photonic 1 year.
Almost a year. Not quite. Yep.
Did you work in something related to this, or was it something different?
Oh, something completely different. I did software engineering.
Interesting.
Yeah. I switched gears completely to hardware.
So you did your master's in software engineering?
I did my master's in like quantum information.
Okay.
Yeah.
Okay, very cool.
Yeah.
Yeah, it was very nice talk.
Thank you.
Yeah. Thank you.
Okay.
Thank you, Marcus.